In this video, I will discuss the ways in which heat can be transferred. Heat is transferred from one object to another because of a difference in temperature. Heat can be transferred in one of three ways: conduction, convection, or radiation. We will develop each of these concepts, beginning with conduction. Conduction is the type of heat transfer that takes place when you stick a poker in a fire, a spoon in a bowl of hot soup, or step on a cold tile floor. Conduction takes place due to molecular collisions. Consider an object in which the two ends are at different temperatures. The left side is hot, T1, and the right side cold, T2. But as in the case of placing a poker in a fire, we know these temperatures don't stay like this for long. The cold side becomes hotter very quickly. But how does this happen? When a material heats up, the molecules inside begin vibrating at a faster rate. These molecules collide with the adjacent molecules, causing their speed to increase. Then those molecules vibrating at a faster rate collide with the next adjacent molecules, increasing their speed and temperature all the way down the material, until all the molecules are vibrating at a faster rate and the whole material is hot. This takes place because there's a transfer of kinetic energy of the molecules. In metals in particular, it's the collision of free electrons that causes heat to be transferred throughout the material. It's important that conduction will only take place if there's a difference in temperature in the material, and if some of the molecules are moving faster, on average, than other molecules within the material. Some materials conduct heat or allow heat to travel throughout more quickly than others. We can determine the rate of heat transfer by conduction, or heat over time. A rate is something time. Consider the picture shown. Two objects at two different temperatures, T1 and T2, are separated by a material which allows heat to flow through it, that has a cross-sectional area A and a length L. The rate of heat transfer, or heat over time, can be calculated using the following formula. Obviously, A is area, L is length, T1 and T2 are the temperatures, but K is known as the thermal conductivity, which is a characteristic of the material. The values for thermal conductivity can be found on page 396 of your textbook and are given in two different sets of units. We are interested in using the values measured in units of joules per second meter degree Celsius. This way, we will need to make sure our temperatures are in degrees Celsius, length in meters, and area in meters squared. There are different values for K because each material conducts heat or allows heat to travel through it differently. A material with a high K conducts heat rapidly. These materials are known as conductors. A material with a low K value is a poor conductor, meaning that heat does not travel through it rapidly. These materials are known as insulators. An example which highlights the difference between materials with a high K and a low K is the difference in perceived temperatures of a floor when walking on carpet versus tile that's at the same temperature. Even if these two types of floor are at the same temperature, a person will always perceive the tile as being colder. This is because tile has a high K value, meaning it's a good conductor of heat. Because your foot and the tile are at different temperatures, heat will be transferred. Most people would assume that cold from the tile is transferred to your foot, but it's not. Instead, heat from your foot is pulled away through the tile. happens very rapidly. So because heat's being pulled from your foot, you have the perception of cold. However, stepping on carpet that's at the same temperature feels warmer. Heat is still being pulled from your foot to the carpet because most likely your foot is at a higher temperature than the floor, but it doesn't happen as rapidly, so it feels warmer. So the K value largely determines the rate or how quickly heat transfer takes place. The units for rate of conduction, or Q over T, are joules per second. You may recall that a joule per second is also a watt, the unit for power. So rate of heat transfer is sometimes referred to as power, but usually is just denoted as rate of heat transfer. Let's try a practice problem on conduction. One end of a 33 centimeter long aluminum rod with a diameter of 2 centimeters is kept at 460 degrees Celsius, and the other end is immersed in water at 22 degrees Celsius. Calculate the heat conduction rate along the rod. Pause the video for time to work on the solution. We know that rate of heat conduction is calculated using this formula, but we're not explicitly given the area, so we have to find the area. We'll use the diameter that's given, 2 centimeters, and change it to, so 0.02 meters. Then we'll change that diameter to a radius, cutting it in half, to get 0.01 meters, and then finding the cross-sectional area, we have pi r squared. So pi times 0.01 meters squared will give us the area. We have the K value, we now have the area, we have the two temps of the aluminum rod on either side, and we have the length. So we plug in, and we solve for the rate of heat transfer, Q over T, which is 83.4 joules per second, or, again, joule per second is the same as a watt. The second method of heat transfer is known as convection, which is the type of heat transfer that takes place particularly in liquids and gases. Convection is heat transfer that takes place by the mass movement of molecules due to density differences. One example that highlights convection is water on a stove. The stove transfers heat to the pot, and the pot transfers heat to the water. Most of the heat from the pot transfers to the water at the bottom of the pot. As the liquid heats up, the molecules begin to move faster and move further apart, decreasing the density of the water. As a material becomes less dense, it floats upward. When the water reaches the top, it's no longer receiving as much heat, and as a result, cools very slightly. As the liquid cools, the molecules move slower, arrange themselves a bit closer together, and the material becomes more dense. A more dense material will sink, so the water sinks back to the bottom, where it's heated again for the entire cycle to start over. This cyclical type of movement is known as a convection cell, or convection current. As a result of the convection currents, the material will continue to get warmer and warmer as it undergoes this cyclical type of motion. Again, convection is heat transfer due to the mass movement of molecules caused by density differences. This is different from conduction because it's a mass movement of molecules throughout the entire material, whereas conduction is more of a vibration of molecules in somewhat fixed positions, bumping into adjacent molecules, not actually moving throughout the entire material. much like the example of a pot of water on a stove, convection currents also take place within the Earth's asthenosphere, the liquid part of the mantle. Heat comes from the interior of the Earth and warms the mantle so that part of it begins to melt into a semi-liquid form. As the mantle warms, it becomes less dense and rises. When the mantle rises further from the interior of the Earth, it cools down, becomes more dense, and sinks. These convection cells or convection currents can cause the lithospheric or tectonic plates to move toward each other, away from each other, or even side to side, creating things like mountains, trenches, volcanoes, and even earthquakes. Convection also takes place within your home. Most heat comes from the floor. Whether you have heat ducts, a space heater, or even radiant heat in the flooring, the type that's built right into the floor. This is because the source of heat will warm the lower air, causing it to become less dense, rise, cool back down, become more dense, fall, and then warm again. This is also why most air conditioning units, aside from those placed in windows, are placed up high. These units depend on the cool air entering the room, and because it's cool, it's more dense. It falls immediately as it enters the room because it's more dense, warms at the floor, rises, and then cools again as it makes contact with the cool air entering the room, up high. You probably aren't even aware that the air actually circulates in these convection currents. Ocean currents and wind are also driven by this type of convection cell. Conduction and convection have one important similarity. Both require the presence of matter, or a medium. Conduction needs matter because it's the matter or the molecules that actually vibrate and bump into each other. If there's no matter, no molecules, then there's nothing to actually transfer the heat. Convection requires matter because it's the actual material that becomes more or less dense, undergoing the convection current. If there's no matter, then convection will not take place. So, because conduction and convection require the presence of matter, these types of heat transfer cannot take place in a vacuum. A third type of heat transfer, known as radiation, does not require a medium or matter in order for heat to be transferred. Radiation occurs when heat travels as electromagnetic waves, such as those that travel from the sun to the earth, through empty or nearly empty space, which is known as a vacuum. Examples of such electromagnetic waves are visible, infrared, and ultraviolet waves. Some materials radiate energy more than others. To determine the rate at which an object radiates energy, we use an equation called the Boltzmann equation, which states that delta Q over delta T is equal to sigma EA T to the fourth. It is only the temperature that's raised to the fourth power. So what do all these symbols mean? Well, A is area, meaning the larger area, the more it can radiate energy or heat outward. T is obviously temperature, and in this case, must be measured in Kelvin. And the larger the temperature, the more it radiates heat. Sigma is a constant known as the Stefan-Boltzmann constant, which has a value of 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth. And finally, E stands or the emissivity, which is a characteristic of the material surface. The emissivity value ranges from 0 to 1. A high emissivity of 1, or near 1, means that heat is radiated very well, which takes place with black surfaces such as charcoal or a cast iron wood stove. A low emissivity, near 0, means that heat is not radiated very well. Surfaces such as metals have low emissivity and do not radiate heat well. Shiny surfaces emit less radiation, and we know they absorb less heat energy because more heat will be reflected off of a shiny surface. Black surfaces will emit more radiation and therefore can absorb more radiation, meaning that very little heat or energy is reflected. This is why you are more comfortable wearing light or white-colored clothing on a hot, sunny day. The white surface reflects much of the heat energy, and very little heat is absorbed. If you're wearing a black or dark-colored piece of clothing, it will absorb more of the heat energy because very little will be reflected, and it will seem hotter. A good absorber is always a good emitter, and a good absorber will always be a poor reflector. If it's absorbing well, then it's not reflecting well. If it's reflecting well, then it's not absorbing well. The previous equation for rate of radiation refers to the rate of radiation given off by one object. But if energy is given off by one object, it must be absorbed by another. Heat is always exchanged between two objects. We can determine the net or amount of radiation transmitted between two objects. Consider an object at a temperature T1 and its surroundings at a temperature of T2. The object can radiate heat to the surroundings equal to Q1 over T. At the same time, regardless of temperatures, the surroundings will transmit energy to the object equal to Q2 over T. So the net rate of radiation between the two objects is equal to sigma EA, and then in parentheses, T1 to the fourth minus T2 to the fourth. Based on the temperatures of the two objects, we can determine if the net energy is transferred to the object or to the surroundings. For example, if the temperatures are equal, T1 equals T2, then plugging in T1 and T2 in the equation, we'll see that the value in parentheses will become 0, and any numbers times 0 will give us an answer of 0. So, the net rate of radiation in this case will be 0. This means that the objects are in thermal equilibrium, and there is no net heat flow. But this does not mean that heat doesn't flow, period. It just means that the object is radiating heat to the surroundings at a given rate, and the surroundings must be radiating heat to the object at the same rate. There's no net heat flow. But if T1 is greater than 2, the net heat flow is from the object to the surroundings, because heat flows from the higher temperature to the lower temperature. The net heat flow will turn out to be positive, and as a result, the object will cool and the surroundings will warm, because heat is leaving the object going to the surroundings. If T1 is less than T2, the net heat flow is from the surroundings to the object, because heat flows from the higher temperature to the lower temperature, and the net heat flow will be negative, meaning the object will warm and the surroundings will cool. object which is capable of radiating energy, but we can use the Stefan-Boltzmann equation to determine the rate of radiation. Instead, we treat the sun as a separate source of radiation. It has been found experimentally that about 1,350 joules of energy strikes the atmosphere of the Earth from the sun per second per square meter. This value is known as the solar constant. However, the atmosphere absorbs about 70% of the energy from the sun before it reaches the ground, depending on cloud cover. For all of our calculations, we will use a value of 1,000 watts per meter squared, which refers to the amount of energy that strikes the Earth's surface on a clear day. To determine the rate of radiation by the sun, or heating by the sun, consider our sunbathing duck. The sun's rays are radiated through empty space, through Earth's atmosphere, and then are incident upon the duck. We will use the surface area of the duck, which we will estimate as a rectangle with surface area A. It is also important that we establish a coordinate system, an X and Y system. The sun's rays make an angle theta with the vertical or the y-axis. We can calculate the rate of radiation by the sun using the formula delta Q over delta T, or rate of radiation, equals 1,000 watts per meter squared times EA cosine theta. So where does the rest of this equation come from? Well, we know E is the emissivity, and it tells us about how well that object will absorb or emit radiation. In this case, absorb it. And A cos theta is known as the effective area, the area that is at right angles to the sun's rays. So how is this shown? Well, because the rays don't strike the surface of the object exactly perpendicular, or at a 90-degree angle, we need to find the effective area, the area that is perpendicular to the sun's rays, which looks like this. Because of alternate interior angles, theta is also the angle between the horizontal axis and the effective area. So the effective area, that blue line, is equal to A times the cosine of theta. One example which highlights the concept of effective area is the change in seasons on Earth. You may recall from Earth science that it's not the changing distance from the sun that causes changing seasons. The seasons change as a result of the tilt of Earth's axis. In the summer, in the northern hemisphere, the northern hemisphere and North Pole are tilted toward the sun, so the rays hit the surface of the Earth more directly. In the winter, the northern hemisphere is tilted away from the sun, and rays strike the surface indirectly. This can be more apparent in the next picture. In the summer, because the Earth is tilted toward the sun is hot in the sky, and the rays strike the Earth's surface more directly. In the spring and fall, the rays are a little less direct, and in the winter, the sun is the lowest in the sky, so the rays strike even more indirectly. Because of the change in location of the sun in the sky, the angle at which the rays strike the ground changes. The smaller the angle with the vertical, the more direct the rays are, as in summer, and delta Q over T, or the rate of radiation, is higher. So Earth heats well. The larger the angle with the vertical, as in winter, the less direct the rays are. and delta Q over delta T, or rate of radiation, is going to be lower. So the Earth doesn't heat well in the winter. Another example that highlights this relationship is the use of solar panels to convert solar energy as electromagnetic waves into electrical energy. The angle at which the sun strikes the surface of the panels determines how much current or electricity is produced. The more direct the sun's rays, the more an electricity will be produced. If you laid a solar panel down horizontally or flat on the ground, the sun's rays would strike the solar panel indirectly at a large angle with the vertical. So the effective area would change. Now, by tilting the panels at an angle, the sun's rays strike more directly, increasing the overall effective area and increasing the amount of radiation or rate of radiation. Most panels in the New York area have to be tilted at an angle of about 42 degrees. The pitch of a roof is very conducive to increasing the overall effective area because it's very close, usually, to this 42-degree angle. Let's try an example. How much power is radiated by a tungsten sphere with an emissivity of 0.35, which has a radius of 22 centimeters and a temperature of 5 degrees Celsius? And also, if the sphere is enclosed in a room whose walls are kept at -5 degrees Celsius, what is the net flow rate of energy out of the sphere? Pause the video for time to work on the solution. Part A asks us to determine the rate of radiation, or the power, which in this case is equal to sigma EA T to the fourth. We have to find the area first, and in this case, it's the surface area of a sphere. From geometry, you may recall, or just based on looking it up, the area of a sphere is 4 pi r squared. The radius was 22 centimeters, needs to be converted to meters, so we get 0.22 meters. Square that, and then multiply it by 4 pi, we get an area of 0.608 meters squared. We can also use the temperature in Kelvin, which has to be converted from the degrees Celsius temperature. So we take the degrees Celsius temperature and add 273, which gives us a value of 298 Kelvin. Finally, we can plug into our equation. We have every other piece. Sigma is the Stefan-Boltzmann constant. E is 0.35, area and temperature we just found. Make sure you notice the brackets around the temperature to the fourth. It is only the temperature that gets raised to the fourth power, not the entire quantity. And our answer will be 95.15 watts, or 95.15 joules per second. Part B, we're looking for the net rate of radiation. And so we have sigma and E and A, which are the same from before. And now in parentheses, we have T1 to the fourth minus T2 to the fourth. Well, we already know what T1 is. It's the 298 Kelvin from Part A. T2 is the walls of the room, which are kept at -5 degrees Celsius. Needing to convert that to Kelvin, we add 273, and the temperature 2 comes out to be 268 Kelvin. So then we can plug in all other values. And notice again, in the parentheses, we have T1 raised to the fourth power, then subtract T2, which is also raised to the fourth power. And we find the net heat, or net rate of radiation, to be 32.9 joules per second, or 32.9 watts. Here's our last problem. What is the rate of radiation from the sun on a block of ice at 0 degrees Celsius with a flat horizontal area of 1 meter squared and a thickness of 1 centimeter. Assume that the sun's rays make an angle of 30 degrees with vertical and that the emissivity of ice is 0.05. Also, determine how long it would take to melt the entire ice cube. Pause the video for time to work on the solution. And here's our answer. Part A, we find the rate of radiation by the sun using the second equation for rate of radiation, 1,000 watts per meter squared times EA cos theta. We have the emissivity value, 0.05. The area was given to us, 1 meter squared, and the angle that the sun's rays make with the vertical is 30 degrees, so that's our theta that we plug in. And we find the rate of radiation to be 43.3 joules per second. Part B, we need to figure out how long it takes to actually melt the ice down. Well, we just saw that the rate of radiation is 43.3 joules per second, and that's delta Q over delta T. Well, we're actually going to solve for the delta T. And to do that, we have to know how much heat is actually required to melt the ice. Q, when melting, is equal to mass times the latent heat of fusion. Well, we already know the latent heat of fusion, but we aren't given the mass. However, we were given the volume, kind of, in a way. We had the thickness, and we have the area. So, if we kind of have the volume, then we can say that mass is equal to density times volume. And the volume is length times width times height. Well, volume is length times width times height. We already have the length times width. That's the area, 1 meter squared. And then the height we'll call the thickness, 0.01 meters. So multiplying those two together, the area times the thickness, we find the volume to be 0.01 meters cubed. Now to find the mass, kind of backtracking a little bit, it's equal to the density times the volume. We just found the volume, 0.01 meters cubed, and the density of ice we can look up. It's 917 kilograms per meter cubed. Multiplying the density times volume, we get the mass to be 9.17 kilograms. Last little step before we actually solve the problem. Q is equal to mass times the latent heat of fusion. Mass we just found, 9.17 kilograms, and the latent heat of fusion is 333,000 joules per kilogram. So, multiplying the two, we get Q to be 3,610 joules. And back to our original problem for part B, delta Q over delta T is 43.3 joules per second. We just found the delta Q, which is 3,053,610 joules. Put that over time, and then set that equal to the rate of radiation, 43.3 joules per second. And then we solve for delta T. So we multiply both sides by T and divide by 43.3. We get the time to be 70,522.2 seconds. We could convert that into other units as well. You can leave it as seconds, but if you want to go a little further and figure out what that time really means, we can change the seconds to minutes by dividing by 60 seconds per minute. And we get 1,175.4 minutes. We can then change the minutes to hours by dividing by 60 again, and we find the time to be 19.59 hours.